Hello, everyone. Thank you very much for joining the talk. I'm pleasure to share Instacart's journey to real-time machine learning in the MLOps World Conference. I'm Guanghua Shu, and I build the end-to-end machine learning solutions with algorithms and systems code optimization. And my current focus is basically on the e-commerce applications at Instacart. And before actually, let me see. Does it allow me to go to next slide? Okay. Yeah, before the main talk, I would like to acknowledge the colleagues who have contributed this journey. This is a highly cross-functional effort among ML Foundation, data engineering, and application teams. So here's the agenda for today's talk. I'll start with a brief introduction about machine learning at Instacart in general. Before zooming into real-time machine learning, I'll explain why real-time machine learning is needed at Instacart. And after that, we'll dive into details about the infrastructures that we have built to enable the transitions to real-time machine learning. We'll also highlight some use cases, see how they benefited from the real-time machine learning platform before wrapping up the talk. Let's get started with an ML at Instacart. Hopefully you have heard Instacart, or some even may place the orders through our platforms. Instacart is a leading grocery technology company in North America, and our value proposition is very straightforward. We run an online platform to deliver groceries and also many non-grocery items from stores that you already love to your doorsteps in as fast as 30 minutes. So at its core, Instacart's business is a four-sided marketplace. We connect customers to a personal shoppers who deliver the service in real time. And we also partner with local retailers to give customer access to local stores they're familiar with. We also offer coupons and other incentives from the brand partners that uses the ads platforms so that we can lower the cost of the items that you can purchase on the website. So machine learning is basically applied in almost every edge in this graph, such as item availability for inventory prediction, search, advertisement, and fulfillment. And we're actually going into details of some use case in later part of the talk. We also have some new offerings such as Instacart for Business, Instacart Health, or Caper Card. All of them are leveraging ML extensively and operate in harmony with the four-sided marketplace. Here's some high-level statistics to summarize ML at Instacart, and it helps probably to keep some of them in mind throughout the talk as we discuss the scale, such as about 1 billion product items in catalog, and we're supporting about 600K shoppers and millions of users, and more than 1,400 retailers on the marketplace, and over 5,500 brand partners that leverage our advertisement platforms to connect to the customers. So enough for the basics of ML at Instacart. Let's now zoom into real-time machine learning. The first question is why real-time machine learning is needed. I think it's helpful to set up the discussion with the context of a shopping journey at Instacart. And we start with the journey that when batch ML is in operation. But the basic business is customers start placing orders in our platforms, and it can request the order to be delivered in as fast as 30 minutes, as we mentioned before. And shoppers go online to fulfill the order based on the catalog availabilities at different retailers. And shoppers and customers can actually interact through the app during the shopping process to either do item replacement or do adjustment to the orders when necessary. And all through this process, the advertisements from our brand partners and various coupons and incentive offers could also target at different steps to make sure the customer can enjoy an inspirational shopping journey. Many of these actions happen in real time, as you can see, and any additional latencies in response could worsen the customer experience. And unfortunately, as I will review in next slides, that our initial batch-oriented ML systems can actually hit some limitations in optimizing this shopping journey. Looking back, it is actually natural choice for companies to start with batch-oriented ML systems, as shown in this slide, since the progress can be actually bootstrapped by the existing infrastructures. Generally, it is probably simple to build and easy to operate a batch-oriented ML systems. And the cost is often lower because there's already something existing that can be leveraged. And for the companies that are relatively early in the ML journey, the performance of the batch ML system is likely good enough. And ML system at Instacart, as I mentioned, also started with batch-oriented systems with two main characteristics. I mean, the first one is basically models only had access to batch features that from historical data that either computed daily or weekly or whichever period that is needed, but it's not real-time in-session data. And also, these models pre-compute the predictions offline in batches and consume those predictions in lookup fashion. So basically, machine learning engineers could simply write these two database tables, and application can read them in production without the need for complex infrastructures. But over time, we do observe some limitations in such systems, and mainly can be categorized into the three scenarios, at least in Instacart business. First, we notice that there are scenarios that response lags that will lead to inferior user experience. And the lags usually come because of two reasons. One is response are pre-computed based on requests happened in the past. And second is response actually does not consider the real-time in-session signals. And secondly is there's actually the fair amount of waste that increased unnecessary costs. Let me give an example. Usually that not all customers will be active in our platforms. And for pre-compute the prediction result, we actually need to compute that result for all users every day. And that's actually a waste in both in terms of computation and storage resource. And thirdly is usually we call it limited coverage, but it's that leads inherent kind of compromise in the systems. So a very common example is, let's say we want to do user product recommendation to users. And it's usually not possible to cache the predictions for all the user and item pairs because of the large cardinality. Recall that we have millions of users and billions of product items. And the product of those is just unmanageable to store those for fast lookup. So we ended up have to truncate, at least in the tail, and this leads to limited coverage in recommendations, and the result becomes less personalized, and the shopping journey becomes less inspirational in general. So I think in all these three scenarios, you can see the limit in the batch ML system, and then we will discuss in the rest of the talk that the real-time ML systems can actually resolve these issues and then perform better. So I think hopefully you summarize that we at least need three characteristics for the real-time systems. It needs to be more responsive, and it needs to be more contextual, and hopefully it can reduce the waste and reduce the cost. So then the important next question is, how do we actually transition the batched ML systems into a real-time ML system to have these important characteristics. And we have done this transition in 2 phases. Among other things, I think the 2 major transitions we have done to enable real-time ML is, first one is real-time serving or real-time prediction. It's basically shifting from serving the pre-computed model predictions to serve the models real time to respond to the incoming request. And this will basically reduce the staleness and limit coverage. And also, the second is real-time features. And this is basically adding the real-time signals into the existing batch signal so that the data is more fresh, and then the model can respond to changes in real time. So let's dive into the details of each transition, actually. So starting with the transition from offline pre-computation to real-time serving and predictions. The transition to real-time serving there are many other things. I think the largely 2 things I want to list out here is 2 main products. One is feature store, and the other is online inference platform, or sometimes we call model serving platforms. We'll cover the details of each shortly. But at a very high level, the feature store builds the connection between data and ML models and enables sharing of features across different models. And model serving platforms enables online inference or real-time prediction. And it streamlines the model deployment and serving and make the model to be more responsive. So specifically for the feature store, it converts the raw data into features that is ready for ML model to consume, either for training or serving. It builds the connection between data and model, and that's literally what it means. And also standardize the feature transformation and feature storage and feature access process. And more importantly, the same pipelines for processing the features are applied in both the offline store, which is we store features for model training, and the online store for model serving to eliminate potential skills between training and serving that usually is kind of very hard debug issues that if it happens in production. And it also allows us to share features across models, and the process is basically managed more efficiently with versioning of features and backfill and etc. So, and for the second piece about the model serving platforms, as mentioned, it is streamlined deployment and serving tasks in the model management lifecycle in general, as described in this slide. Basically, the middle deployment plus the serving steps is what we meant by model serving platforms. So the infrastructure becomes more complex with such a platform. As you can see, that includes the MSP workers, feature store, then you have serving sidecar containers, and also the control plane to enable the real-time predictions. And of course, it comes also with higher operational overhead. So in order to operate such complex system efficiently and reliably, we adopted a unified interface for machine learning engineers to have a consistent entry point to the systems. It basically means that it's a consistent that UI layer or API layer to be integrated in service or through the console operations, so that all the backend details are hidden away, and so that the machine learning engineers, when they actually use it, does not need to deal with the details. And then also we standardize the RPCs for communications among the services within the systems to make sure that the system is more manageable and reliable. So we also, I think the benefits we get such, although it's more complex, I think the benefits we get from MSP are also encouraging. First of all, MSP actually improved the engineer productivity a lot by reducing the model serving setup time from a week to less than an hour. But that's what I mean, that before we have this model serving platforms, once we have the model chain, to till the point that we set up the ML services, we actually, for building the ML services, we actually will need a week of time actually to just build the service. But with this, the consistent entry point will just allow users to, with some configuration-based setup, and then click off some UI, buttons in the UI to actually just generate the endpoint for model serving, and that's it. So I think that's actually a huge lift in terms of productivity. And also, as we mentioned before, the ML services itself now becomes more efficient by only, because it's serving online, it's only computing then the necessary results in real-time prediction. They also become more responsible by incorporating the real-time features. That's what we'll be describing next. So yeah, this brings us to the second transition, which is basically enable the real-time features. So in the previous transition, we have described that now we can serve the models in real time. That improves the user experience by eliminating the staleness, and also limited coverage of, and also reduce the limited coverage issue of pre-computed predictions. But there's still one thing that the predictions and all that is still based on the batch features that is generated in daily or weekly. So the second transition is to aim to bring the best experience in the shopping journey. It actually requires us to have both batch features and real-time features. And to enable this, we have developed the real-time features pipeline with streaming infrastructures as shown in these diagrams. And we will show streaming structures in a bit more detail in next slides. But the pipeline basically listens to the raw events published through Kafka and transform them into design features using Flink to do the computation, and then sync them into the feature store. And then after that point, it becomes basically whenever the services needed to access such features, both batch features and real-time features, they're all available. And the latency of this is usually in the order of seconds. And yeah, as I mentioned, this slide basically describes the high-level architectures of the streaming infrastructure. And the architecture, you can think that this is I think it was mentioned in a blog post that it's basically built around Kafka for centralized event storage and Flink for computation. And of course, it also have these things at the beginning, and it will have the event proxy that ingest events from both external clients and the internal services to Kafka. And then after Flink has processed the features, it also syncs the processed events into different destinations, such as data warehouse for general operations, and ClickHouse for real-time analytics, and feature store for ML use cases. And we named the Flink platforms Cheetah, and you might have heard in some of our blog posts on there. And it basically, there are many aspects of this. What I want to highlight in this talk is that it incorporates a config-based job definition to enable self-serve, and also support 2 layers of abstraction to define the transformation logic, namely Flink SQL and the data stream API from Flink. And of course, we won't have time to go to all the details of this streaming infrastructure in this talk. What I wanted to give an example in the next slides to show that how Cheetah can help in ML use cases to improve the productivity by making the creation of the real-time features to be much easier. So concretely, this is a YAML configuration file that defines a Flink job in Cheetah to extract users' last K recipe view from the raw events. Basically, recipe view is the raw events. And it contains three main parts: the source session that defines raw events, and the sync session defines the destination that it links right to. And then the processor section is basically the Flink SQL logic to extract the last K recipe views from the raw events, and to help with the tasks such as session-based recommendation and or similar tasks. And this config-based approach, you can first of all, it actually greatly reduces the learning curves about setting up the real-time features, because it strips out away the barriers, a lot of the streaming infrastructures that you need to write Java, Scala code, or actually you need to kind of set up a lot of infrastructures to actually just even beginning to write the code. So I think the config and the notebook along with it basically helps to lift that up so that the users only need to focus more on the logic that they want to do. And also, furthermore, Cheetah develops very powerful user-defined functions to further simplify the code and improve readability. For example, it actually built in UDF like last K views, and if you give the page ID and timestamp and how many views you want, in this example it's 10, and it actually will extract that from the raw events. And then, this function is basically extracted the different data types from the JSON raw event payload. So since this actually makes the together, makes the real-time feature definition to be much easier, and used to take weeks now. For the ones who are familiar with this, it actually only take hours to actually define the real-time features and test it. And yeah, I think we have discussed two main transitions. Putting everything together, I think we basically have built a kind of real-time ML flywheel. As you might recall at the beginning, we reviewed the shopping journey with the batch system. Now, what we added more is basically the streaming infrastructure, leveraging the streaming infrastructure to define the real-time features and streaming into feature store. And then so that the models can use these features directly in order of the seconds. So overall, the real-time ML flows terabytes of data per day now, and it's growing and generates features with latencies in order of seconds, as I mentioned, compared to hours before, and serves hundreds of models in real time. And the platform actually resolves a lot of limitations. Hopefully, you would agree at this point that we can see in the batch-oriented ML systems. And I would like to show some of the use cases that see how such a platform can actually help the ML services to actually be more responsible and actually generate business impact. So use case highlight. And since the inception of the real-time ML platforms, it has been adopted by a diverse set of the ML services. I listed some of them here. It ranges from the item availability for inventory predictions and fulfillment, batching optimizations, and to the recommender systems, services in recommender systems such as a session-based recommendation, query understanding, and etc. And also even for fraud detection. I think we cannot touch everything. I think we may have probably time to review 3 of them. I highlighted in green. I quickly go through them and to see if the design resonates with you. So starting with the real-time item availability. The service basically updates the item availability scores with the goal to improve the found rate and fill rate, and also reduce bad orders. So in addition to the historical data, what real-time ML platform can provide is actually signals such as the shopper's real-time in-store signals. And then also some retailers, they provide like API access to the inventory update, although not very consistent, but with a little less delay. So as a result, actually the model responsiveness actually improves a lot, at least for the shopper signals that actually we can get the visibility into the signals in the order of seconds. And actually the services after adding the real-time component has created this significant business impact. So before switching to the next use case, I'd like to take a look at an interesting example about the not found signals and reported by the in-store shoppers. It actually can help us estimate the restocking to share time for certain retailers, as shown in these diagrams. So in this example, it takes about 8 minutes for the restocking the bananas for certain retailers. Basically, after about 8 minutes, the not found signal basically kind of dies away since it has first time been reported by the shopper groups. So, and this is actually one of the key insights that the models have been leveraging to build the real-time item availability signals. And you can find more details about this in the blog post. And onto the online and query understanding service. The service obviously aims to understand users' intent by extracting semantic meanings from the query. But previously, in the batch-oriented systems, the service basically serves pre-computed query classification results and also do key value lookups for query embeddings. And with the transition to real-time ML, the service now is able to serve the query classification model online because the model is relatively small for all the queries. And this basically cuts the requirement to store the pre-computed result in memory. And for embeddings, here we kind of taking a hybrid approach. Is for popular queries, we do key value lookup to reduce the latency. But for less popular queries, because computation is not very often, we actually just leverage the transformer models to directly do the computation. So that it helps actually to reduce the memory requirement at this point. So I think it's through the kind of the real-time platform enablement, we actually not only improve the latency of the online QoS service, but actually also reduces resource consumption as well. So, and I think lastly, we're a bit short on time. I'll go quickly on this one. So lastly is a contextual recommendation. This is actually a very popular use case for real-time ML. Here is an example describing how it works in Instacart. It follows similar logic as a sequence modeling. For example, given a recently viewed history of pancakes, eggs, and bacon, we could infer that user is searching for breakfast items. And our model would learn that user might be wanting to complete their breakfast with milk, orange, and juice. And furthermore, since the sequence encodes product characteristics such as organic or vegan, the model actually will naturally learn to incorporate this information into its recommendation. Therefore, recommendation will not only be more relevant, but also be more personalized to users. And this actually has been tested in many services in our product and actually has been retrieved wins in multiple services. And also in recent development, it has also showed effectiveness in personalized the LLM prompts in the Ask Instacart service. So for folks who might like to want to understand a bit more, this slide basically gives a glance about how model actually trained for contextual model in ads. It includes basically pre-training and fine-tuning steps. As depicted on the left is basically the pre-training steps. we uses the unsupervised learning with denoising objectives. It's basically similar to masked language model. In this approach, we basically taken an input sequence and randomly cropped it. And then the model's goal is then to predict the original sequence from the cropped version. And then after pre-training, the fine-tuning objective to predict the next item to be added into the cart. This is what we will want from the final model. And the input sequence of this is the products that's already added in the shopping cart. And after training, we will basically evaluate these models as normal, like in offline with the normal ranking metrics and followed by A/B experiment. This actually turns out to be one of the biggest wins in Instacart ads. So I think we're almost at time. I think for takeaways, basically, I think we discussed that 3 scenarios that real-time ML will help. And for customer-facing applications, that is likely the case. And also, by building the transitions, what we learned is basically that we need to pay close attention since the infrastructure plays a crucial role in this, especially in real-time machine learning. And if you need such transitions, you need to kind of plan a reasonable investment on it and then building best practices early on. And then make incremental progress so that you can have continuous investment and also grow the product with the hero use cases early on so that actually help the platform adoption with happy early users. I think this wraps up my talk. Sorry for going a bit over. And this list of references will help you get more details about the platform and then use cases. And I can stay a bit more to answer some of the questions, but folks, please feel free to sign off if you need to attend the other sessions. I think in terms of the questions, I just go through the ones that in the channel. How did you avoid training and serving data skill? Yeah, I think this question arises when we discuss the feature store. Mainly what in terms of the skill, what we can avoid is the skill introduced by logic difference. What I mean is during the training, the path to the offline store and the path to the online store, if everything goes to feature store's processing pipeline, then the same logic will apply to them. So then there's no logic differences in terms of creating those features. But if it's a skill because of the time or because of the distribution shift in the data, then a common pipeline won't be able to address those kind of skills. Yeah, so thanks for the insightful talk. The slides remember. Yeah, I think I can try to make it available. I work with the conference organizers to see what's the best way to share. And related to question about training and serving data skill, how do you handle feature mismatch between the time features are updated in the online feature store and the time model? Yeah, I think for this question, if you mean that the data distribution has been shifted over time, I think feature store won't be able to resolve these problems. What we do in our overall ML platform is basically we keep monitoring the 2 things, the data distributions and then also the model performance. And we basically set up certain threshold. If we detect either the data drift or the enough deterioration of the model performance, and we will trigger an automatic retraining to update the model and then do the evaluation to make sure that the new model have better performance and then deploy it again. So again, I think it's related to the first question. The common pipeline I would describe is basically avoid the logic difference introduce data skill. That is actually something that is very difficult to debug, because if let's say you use different systems to generate features for training and serving, and for then inherently it's kind of difficult to match exactly. Yeah, and that actually does happen in practice. Yeah, how do you handle in testing? Testing unit integration. I think, yeah, this is a very great question. I think in terms of the unit testing, I think a lot of it's close to what Flink SQL would be able to provide. I think what we might do a bit better is, in this case, that we have in the Cheetah platforms, we have a lot of the user-defined functions. We have fully unit tested, and then within the platform itself before release it to users. So at least we know those functions are fully unit tested. But for SQL, I think it's a common problem. So it's kind of difficult to unit test. But yeah, I think that's we can only do by integration tests, meaning that we run the SQL command and then see if the result comes out to be what we expect. Yeah, but for UDFs, we do extensive unit testing. What was the your favorite use cases from? Yeah, for this actually, there are two of them I actually highlighted in the use cases session. The most early one is actually the real-time item availability, because it's just such an important use case for Instacart to actually have the right inventory availability prediction. So that's actually the first use case. And it has ended up being very successful. It actually not only improved the font rate and fill rate, but actually also improved the GTVs of the businesses. So that's why actually a lot of teams get more excited about the real-time ML initiatives. And then the contextual recommendation naturally is everyone is doing. I think real-time availability is kind of unique in Instacart's business, and it fits very well in the real-time ML paradigm. Slides I work with the organizers. Do you need to have enable real-time features? Can we start with simple Flink job and cross-return shifts? Yeah, I think you can certainly do that. I think the only problem is if the ML engineers, all the teams that who are involved in the project have the capabilities for either use can set up run the Flink, have background on that, either Flink or other streaming tools. Then I think it's to start with. Obviously, we also start from that. One or two easy jobs to see how it goes. But I think in terms of to scale it up for more machine learning use cases to leverage real-time features, it just becomes very unscalable if every time that everyone has to start from the very beginning in terms of infrastructure setup, and in terms of also the UDFs that we have described before. Those UDFs are actually very common as well. So that actually calls for kind of a Flink platform to kind of package those things so that the effort can be basically multiplicative factors for the things later on. But if you just started, I think it's and you're flexible to catch it, just set up everything by yourself. I think it just run Flink jobs. There's no problem to do that. Yeah. I think I have covered all the questions, and thank you everyone for attending the session. Hopefully it's helpful. And if you have further questions, you can feel free to reach out to me either through LinkedIn or through the emails I have in this platform. Yeah, thank you.